All right, so what we are doing now is discussing trig identities. Some of the main ones here. We might not use all of them. But we're going to use them because they will help us simplify relations or equations that have maybe some complex trigonometric function combinations in them. And this is one of the kind of beautiful things about trig, is that almost every function can be related back to almost any other function using one of these. And that's, I think it's really cool. It's almost like an Ouroboros, like the entire math loops back on itself. And so, yeah, so we might not use all of them, but at some point or another, whether it's in this class or whether it's in an engineering class later on, you will find use for all of them. So you can see here that these are the 90-degree phase shift ones. We kind of discussed this last time, how cosine and sine are pi over 2 or just 90 degrees out of phase with each other. And so you subtract pi over 2, you get the other one. But it's the exact same thing for tangent and cotangent, secant and cosecant as well. Probably the most useful of these that we'll have, and I'm just going to go ahead and rewrite them, because these things you will use a lot, are the Pythagorean identities. I would suggest that you memorize these. So they are sine square theta plus cosine square theta equals 1. Tangent square theta plus 1 equals secant square theta. And cotangent square theta plus 1 equals cosecant square theta.
So is there any significance to the different functions squared, like sine squared theta?
Yes, actually it's Pythagorean identities because it's literally derived from the Pythagorean formula. A squared plus b squared equals c squared. Where here,
it's like sine squared theta plus cosine squared theta equals 1.
because
since 1 can't be squared, well, 1 can't be squared, it's still going to be 1.
it's still going to be 1.
That's why 1 isn't squared.
And it's on the unit circle, 1 is always the radius, which is the hypotenuse, whenever you draw a right triangle from it. So yeah, that's why it's equal to 1. You got your, you can reorder it to where you have the sine as your y and the cosine as your x. Similar things for secant squared and tangent squared theta. So those are extremely important. Another set that we kind of already touched on, but I would suggest that you memorize them, are the reciprocal identities. So which is that cosecant theta equals 1 over sine theta. Secant theta equals 1 over cosecant theta. Oh, no, sorry. Cosine theta. Sorry. And cotangent theta equals 1 over tangent theta. Also, along with these three, I would remember that tangent can always be rewritten. Do you remember what it can be rewritten as?
Sine over cosine.
Sine over cosine. Good. What about cotangent?
Cotangent is cosecant over secant. Or secant over. No.
Wait, actually, you might be right. But wait, hang on. Think about it just, if tangent is this, then what is cotangent in terms of tangent?
1 over tangent.
1 over that. So it's 1 over sine over cosine, which would mean you would just flip it.
Oh, cosine over sine.
Right. Cosine over sine theta. Good. We already talked about the even-odd identities, meaning that, sine is an odd anti-symmetric function. So if you plug in a negative angle, you're going to get negative sine. Similarly, if cosine is a symmetric function, so if you plug in a negative angle, you just get the same cosine. You probably won't use that as much in the identities or in solving the simplifying the equations, but it's possible. You might use these double angle formulas some. So I'll just, I'm just going to draw a box around the really important ones that you should memorize. These. It's good to memorize all of them, or try to, although I don't have them all memorized. Probably the only ones I really do are these, maybe the even-odd identities, and that's about it. There's no way I memorized the product to sum or sum to product formulas. Those are a little bit much. But anyways, let's use these to solve some problems. So let me... All right. So we have this problem here, this equation. And one thing I'll tell you is when you're solving these types of problems, it'll generally be an equation where you have two sides to them, which is what an equation is. I don't know what I was trying to say. My point is, the strategy when you're doing these types of problems is to focus on one side and manipulate it until it equals the other side.
Gotcha.
So don't mess with the secant. In other words, focus on the more complex side and then use the identities. Yeah. So let's write that out. So one, focus on one side. Manipulate with the identities to match the other. And then write a little check. To show that the proof is completed, I guess. Okay. And yeah, usually you'll want to focus on the more complex side.
So is this like a normal equation to where any changes you make to one side, you have to make to the other side as well?
Yes, except these identities, what we're going to be doing is we're just going to be replacing pieces with equal pieces. So it's kind of almost like multiplying by 1 in a way.
Yeah,
We're-
it's like in the exponent problems where it was like 6 and then whatever the exponent was, and on the other side it was 36. It's like changing that 36 into a 6 squared.
Exactly.
Okay.
Yeah,
So it's
exactly like that.
Changing the form, not changing the value itself.
Exactly. Yeah.
Okay.
So you typically will not be adding or changing the value of one side. You're just changing the form of it. Exactly.
Got it. Okay.
So let's think about what we can do here. And what were you gonna say?
The first thing that I like immediately notice is
Mhm.
that secant is equal to where was it on here? It's on here. Secant, it has a relation to its tangent. Tangent squared.
Yeah, yeah. Okay, I'm gonna give you some hints here.
All right.
So hint number 1. It's often really useful to replace any cotangents and tangents with sines over cosines.
Got it. So,
So yeah, we'll replace the cotangent with cosine over sine.
and then tangent will replace with sine over cosine.
Mm-hmm. Oops. Okay. And now, what do you notice?
Well, if we were to just multiply it out, we would get the first fraction cosine over sine. The sines would cancel, which you get
Mhm.
cosine. On the second one, could we throw in a change of phase and do change cosine of theta, change that to sine of pi over 2 minus theta?
You could do that. That would be valid. But I will say that typically making it to where you have different arguments, it's not going to help you.
Got it.
So, but if we just multiply it out, we have, like you said, sine squared over cosine theta. And then we have secant theta. Now, what does that sine squared make you want to do?
It makes me want to add cosine squared to make it equal to 1, or something along the lines of that.
So,
Using the Pythagorean.
yes. So using the Pythagorean theorem or identity is, I think, useful. But I think there's another way to go about using it rather than doing it that way. Think about just like, rather than adding stuff, trying to just replace stuff. So how could we manipulate this equation to replace the sine squared theta? what could we do to this equation?
We could. Looking at my sheet here.
Let me rephrase the question. If our ultimate goal is to just replace sine square theta,
Yeah.
then what could we manipulate? How could we manipulate this to where we could just replace it with something else?
Well, sine squared theta. Yeah, everything's going in my mind. It's like adding or subtracting or multiplying.
Okay. Well, what if we did this? With this
we move
equation,
the cosine squared theta and switch it out with the 1. Or, so cosine squared theta minus 1 would equal, or sine squared theta minus 1 would equal cosine squared theta.
very close. We do want to move the cosine squared theta over,
Mm-hmm.
but we'll just leave the 1 on the other side. Because then what we get is sine square theta equals 1 minus cosine square theta. And now we have something that's equal to just sine square theta.
Got it.
And now we can just replace 1 minus cosine square theta into our equation. So we get cosine theta plus 1 minus cosine square theta over cosine theta equals secant theta. Okay.
Well, if we can get rid of the cosine squared theta, we can turn 1 over cosine into secant.
We can, exactly. What can we do with this fraction here?
We could multiply out the cosine. I don't think that's the answer, though.
Multiply out the cosine.
Cosine on the bottom.
How do you
Oh,
mean? How do you mean?
Like multiplying by cosine, multiplying both sides by cosine of theta, because then we'd have. But then that would get rid of the fraction. We want the fraction. We just want to move the negative cosine squared theta.
Well, I'll say this. So we have 1 minus cosine square theta on top. And whenever you have addition or subtraction on top, what can you do with the fraction?
Invert it? Or no, not invert. Factor? Or no, not factor.
Sort of. Well, not really factor. We can split it up.
Split, that's what I was thinking. So
Yeah.
we would get the cosine, or the 1 over cosine, and then the cosine squared.
Yeah, exactly.
Over 1.
Yeah. So we get, or not over 1. So they're both over cosine. So whenever you have addition or subtraction on the numerator, remember, you can always split those up into 2 fractions. You still have the same denominator on both of them. I think we had a little bit of confusion about this before, where I think you were trying to do this with the denominator, when you had addition or subtraction on the denominator. You can't do that with the denominator, but with the numerator, you can. And the denominator will stay the same. So we'll get cosine square theta over cosine. Good.
And then
What about this thing?
well, if you've got would the one of the cosines from the top and the cosine from the bottom just cancel, and we get negative cosine.
Exactly. Exactly.
And we've got a positive cosine.
And we got a positive cosine.
Those would cancel, and then it'd just be secant equals secant.
Exactly.
Okay, this is starting to make more sense.
Good. Secant equals secant. And we put a little check because we solved it. And these are my favorite types of problems. I love these because they're like little puzzles.
Yeah.
You put together the pieces and yeah, I love them. Okay. So let's do the next one.
Yeah, it's starting to make more sense now.
Okay. Okay.
And the A is the same as theta, right?
Yeah. Yeah. Actually, technically, it's alpha. It's a Greek letter, but yeah.
Yeah. But like it's just taking the places of.
Yeah. Yeah. It doesn't change anything else. Okay. So now the strategy is to pick the more complicated side, but I mean they're basically equally complex. So which one you want to do?
I'm thinking let's do the right side because the left side it's 1 over something. We can split that up a little little easier. Because if it's in the denominator, you can't split it. So let's try and do that.
So you want to work with the left side because we can split it. Is that what you're saying?
I want to work with the right side because we can't get the hard part done first.
Well, because remember what our goal is we're going to try to leave one side alone.
Oh, okay.
And we leave one side alone.
So if we leave, let's do the left side thing because that's going to be easier to change.
Yes.
Got it.
Yeah.
Okay.
Okay. So yeah, we are, and in fact, I kept on writing equals secant, but what we can do is we can just ignore the right side for now and just write out. That way we don't have to write it every single line. Okay. So what would your first step be, you think?
First step is going to be changing that to 1 over sine and minus cosine over sine.
Okay. 1 over sine alpha minus cosine alpha over sine alpha. Okay.
Then 1 over sine is the same as cosecant. So let's go ahead and switch that out.
Okay.
Change that to cosecant minus cosine over sine.
Okay.
And cosine over sine is equal to cotangent.
It's equal to cotangent,
So let's
exactly.
switch that out as well.
All right. Cool.
And then cotangent is equal to 1 over tangent, and tangent is equal to sine over cosine. But that doesn't leave a 1 plus in front of the cosine. The only way I see that happening is by squaring something. None of these are squared. Less.
So I think you're right. I think we will need some sort of square in here because
Yeah, to get a 1.
Because if we look at our Pythagorean identities, one of them has a cotangent squared and a cosecant squared. So we probably want to get that somehow.
So
The fact that we have a cosecant and a cotangent
Mhm.
tells us that. So it would be, that was cotangent squared alpha plus 1 equals cosecant squared alpha, right?
Mhm.
Okay.
And if we move the cotangent over, we'd be left with just a 1.
Yeah. So we have 1 equals cosecant
squared minus cotangent squared, which is what we have.
close to what we have. Almost.
Oh, it's not squared.
Yeah. So this is where I will give you another hint. Back on the hints page. Hint number 3. It is often useful to try multiplying by a conjugate. To get difference of squares. You know what a difference of squares is?
I know I learned it. I couldn't say it off the top of my head.
Well, just think about it, each word individually. It's a difference, meaning you're subtracting
minus
of squares.
Okay.
So some perfect squares. So you would have like a squared minus b squared.
Okay.
Which, if you look at...
Which would be like Pythagorean.
Exactly.
Gotcha.
So do you know how to... You know what a conjugate is, right?
I think so, yeah. So it's like something you can multiply both of them by, right?
Yes. But like if I have a minus b, what is the conjugate of a minus b?
B minus A, or B, or A plus B.
A plus b, exactly.
That's right. So cosecant plus cotangent would be the conjugate.
Correct. So we would want to multiply it by cosecant alpha minus cotangent alpha.
So would we have to multiply the other side?
But, well, not that, because we don't want to change the other side. So what else could we do?
If we
Oh my God, our time is already almost up.
Damn.
Actually, it is up, but we'll keep going for a
keep
minute.
going.
We'll finish this one.
I don't know.
Well, if you have to multiply one side by something and you can't multiply both sides, then what you have to do is multiply by whatever that thing is over itself, because that's 1.
Oh, so if you did like cosecant over cosecant.
Oh, not quite.
Or cosecant plus cotangent over
Yes.
cosecant plus cotangent.
Yes.
And then that would equal out to 1.
Correct.
Gotcha.
So now we haven't changed the value. This is like one of the only times where I say adding something extra to the equation will help. I don't think I can remember a time where literally adding or subtracting a term on the identity is useful. Maybe very, very rarely, but yeah, usually the only time you want to add something to it is when you're multiplying by a conjugate like this.
Yeah, so then it'd be cosecant minus cotangent times cosecant plus cotangent.
Right.
But, so the cosecant would be squared.
Mm-hmm.
The cotangent would be still negative and squared.
Yep. So that gives us our difference of squares.
That gives us our difference of squares, and then
The cross term, whenever you multiply a conjugate or something by its conjugate, the cross terms cancel.
Cancel.
Yeah. So then
cosecant, or that should all be over 1?
no, because there's nothing on the bottom on this one. So
Oh, it would be over cosecant plus cotangent.
correct.
Gotcha. And then that's the same as 1 over cosecant plus cotangent.
Yep.
And then we could get the cosine and the sine for cotangent. And we could get, we need to get it needs to be sine over 1 plus cosine, right? In the end?
Yes.
Okay. So then, if we did cosecant and turned that into 1 over sine,
Mm-hmm.
and cotangent into sine, or cosine over sine,
Good.
and we've got sine on the bottom of both of those, and we've got our 1 plus cosine on the top.
Mm-hmm.
So then, could we add those?
Yeah. Yeah. Exactly.
And do 1 plus cosine over sine over 1?
1 plus
Or under 1?
cosine. Yep. Exactly. Over sine like that. And now we have 1 over this fraction, which means we can just flip the fraction.
Yeah.
So we get sine alpha over 1 plus cosine alpha. And we got it. Aren't these fun?
Yeah.
I love
Takes
these
a
kind
little
of
bit to
problems.
get hang of it, but
Yeah,
once you
yeah.
got it, it's definitely fun.
All right. Well, that will end our class today.